The USS Iowa was supposed to be unstoppable. When it first cut through the ocean, it represented the absolute peak of American naval engineering, faster than most battleships, heavier than nearly anything afloat, and armed with guns so powerful they could strike targets more than 20 miles away. Each of its 9 massive 16-inch guns could fire a shell weighing 2,700 pounds, a projectile so destructive it could tear through reinforced steel, concrete bunkers, and enemy warships with terrifying ease. On paper, the Iowa wasn't just a battleship, it was dominance made of steel. But hidden beneath that reputation was a problem so dangerous, so quietly ignored, that it threatened to turn the ship into its own worst enemy. Because those same 2,700-pound shells that made the Iowa feared were also powerful enough to destroy it. When a shell left the barrel of one of Iowa's guns, it did so with immense force, traveling at speeds over 2,500 feet per second. The kinetic energy behind that impact was almost unimaginable. Engineers had designed the ship's armor to withstand enemy fire, but there was one scenario they hadn't fully accounted for. What would happen if the physics worked against them? In certain combat conditions, specific angles, distances, and trajectories, Iowa's own shells could come crashing down onto armored sections of the ship with devastating force. Not directly, of course. But in naval warfare, shells didn't always travel in straight lines. At long ranges, they arced high into the sky before descending almost vertically, striking decks and upper armor where protection was thinner. And that's where the flaw lived. The deck armor, though strong by most standards, wasn't designed to consistently withstand the full impact of these massive shells falling from above. In testing simulations and calculations, a disturbing possibility began to emerge. Under the wrong conditions, Iowa's own firepower could penetrate armor that was supposed to protect it. Imagine that for a moment. A ship so powerful, it could accidentally destroy itself. This wasn't the kind of problem that could be ignored, but it also wasn't the kind of problem anyone wanted to admit existed. The Iowa-class battleships were symbols of American strength. Billions of dollars, years of engineering, and national pride were tied into their success. A fundamental flaw in their design wasn't just a technical issue, it was a political and military nightmare. So, instead of being addressed openly, the problem was buried. Quietly discussed in technical circles, minimized in reports, framed as a theoretical edge case rather than an urgent threat. After all, acknowledging it would mean redesigns, delays, and difficult questions about how such a vulnerability had been overlooked in the first place. But physics doesn't care about pride. Deep within the shipyards and laboratories, a handful of engineers and metallurgists began to take a closer look. They studied impact angles, material behavior under extreme stress, and the microscopic structure of the armor itself. And what they found only made the situation more unsettling. It wasn't just about thickness. The steel used in the armor had limits that became dangerously clear under the extreme conditions created by modern naval artillery. At certain velocities and angles, the armor didn't just resist the shell, it failed in ways that were sudden and catastrophic. Cracking, spalling, fragmentation, all happening in fractions of a second. And once that process started, there was no stopping it. A single penetrating hit could send lethal fragments ricocheting inside the ship, turning armored compartments into deadly traps for the crew. The very protection meant to keep sailors safe could become part of the destruction. Yet officially, nothing was wrong. The Iowa continued its operations. The guns were still fired. The tests, at least the ones that were publicly acknowledged, showed acceptable results. On the surface, everything worked exactly as intended. But beneath that surface, tension was growing. because a few people understood the truth. They knew the margin for error was thinner than anyone wanted to admit. They knew in a real battle, with chaos, imperfect angles, and unpredictable conditions, that theoretical flaw could become very real. And if it did, the consequences wouldn't just be damage to steel, it would mean lives. Hundreds of sailors, trusting the armor around them, could suddenly find themselves exposed to a threat no one had warned them about, a threat coming not from the enemy, but from their own guns. This was the silent crisis inside the U.S. Navy. No alarms, no headlines, no public acknowledgement. Just a growing realization buried in reports and calculations that one of the most powerful warships ever built might carry a hidden weakness, one that could only be solved by completely rethinking the very material it was made from. And somewhere in the middle of all this uncertainty, one man had already begun searching for an answer. By the time the first doubts about the Iowa's armor began circulating, most people in the system chose to ignore them. Not because they were careless, but because everything around them discouraged doubt. The ship worked. The numbers looked acceptable. The official reports were reassuring enough. And in an environment where careers, contracts, and national prestige were on the line, raising a serious flaw wasn't just difficult, it was dangerous. But not everyone was willing to look away. Among the engineers and metallurgists working behind the scenes was a man few people paid attention to. His name was Arthur Clark. He wasn't a senior official, not a decorated naval officer, not someone with influence in Washington. He was the kind of specialist who spent more time with data than with people, the kind of man whose work mattered, but whose voice rarely carried far. Clark worked odd hours, often taking the graveyard shift when the labs were quiet and distractions were minimal. While others focused on routine testing and standard procedures, he kept returning to something that didn't sit right. The numbers didn't add up. On paper, the armor should have been strong enough. It met the specifications, it passed controlled tests. But Clark wasn't convinced those tests reflected reality. He began digging deeper, rechecking assumptions, recalculating impact forces, analyzing how steel behaved under extreme stress rather than ideal conditions. What he found was unsettling. The problem wasn't obvious. It wasn't a simple case of armor being too thin or poorly manufactured. It was more subtle, buried in the interaction between velocity, angle, and the internal structure of the metal itself. Under certain conditions, the armor didn't just absorb energy, it failed in a way that amplified the damage. Clark ran the calculations again and again. Each time the conclusion was the same. If a 2,700-pound shell descended at the right angle and speed, it could penetrate sections of the Iowa's protective armor. Not always, not predictably, but often enough to matter. Often enough to turn a rare scenario into a real threat. For Clark, that was enough. He documented his findings carefully, building a case step by step. Charts, equations, material analyses, everything laid out with precision. There was no exaggeration, no speculation, just evidence. Then he did what he was supposed to do. He reported it. At first, the reaction was muted. A few colleagues glanced over the data, nodded politely, and moved on. Some assumed there must be an error. After all, the design had already been reviewed by top experts. Others acknowledged the possibility, but treated it as a low-priority concern. A theoretical issue. An edge case. Nothing urgent. But Clark didn't stop. He refined his analysis, expanded his models, and resubmitted his findings with even more detail. This time, the response was less polite. Questions turned into pushback. Where were his assumptions coming from? Why didn't his conclusions match established models? Was he accounting for all variables? Had he misunderstood the design parameters?
It wasn't outright rejection, not at first. It was something more frustrating. Doubt. Not just about the data, but about him. Clark didn't have the reputation to challenge a system that had already validated itself. The engineers who designed the armor were respected figures. The manufacturers had delivered according to specification. The Navy had already accepted the results. For someone like Clark to suggest a fundamental flaw wasn't just inconvenient, it was disruptive. And disruption wasn't welcome. As the discussions continued, the tone shifted further. The issue was reframed not as a potential vulnerability, but as an overinterpretation. Clark's calculations were described as too conservative, too theoretical, not reflective of real combat conditions. In other words, the problem wasn't the armor, it was the analysis. For many, that was enough to close the case. But Clark couldn't ignore what he had seen. Because for him, this wasn't about being right. It was about what would happen if he was right, and no one acted. He went back to work, this time on his own terms. If the system wouldn't accept the conclusion, maybe it would accept undeniable proof. Clark began exploring not just why the armor failed under certain conditions, but how it could be improved. He studied alloy compositions, heat treatments, structural integrity at the microscopic level. He compared different formulations, looking for patterns others had missed. And slowly, a new idea began to take shape. It wasn't just a fix, it was a completely different approach to the problem, one that challenged existing standards and, if proven correct, would force the entire system to rethink how naval armor was made. But there was a problem. This idea went against everything that had already been approved. It would require new materials, new processes, new testing. It would cost time, money, and credibility. And coming from someone like Clark, it would be even harder to take seriously. Which meant that even if he had the answer, no one was waiting to hear it. So he made a decision. If they wouldn't listen to his warnings, they might listen to results. And that's when the quiet metallurgist working the night shift began a project no one had officially approved. A 12-week effort that would either prove him wrong or change the future of naval warfare.
Clark didn't announce what he was about to do. There were no formal approvals, no official project brief, no team assigned to support him. On paper, nothing had changed. The Iowa's armor was still considered reliable, the issue still classified as theoretical, and the system had already moved on. But Clark hadn't. If the problem was rooted in the behavior of the metal itself, then the solution had to begin there, not with thicker plates, not with minor adjustments, with the material at its core. Steel, as strong as it was, had limits. Under extreme stress, it could become brittle. Under sudden impact, it could fracture in ways that weren't always visible from the outside. What Clark needed wasn't just stronger steel, he needed smarter steel, something that could absorb energy, distribute stress, and resist catastrophic failure even under the worst possible conditions. That meant experimenting with composition. Late at night, when the labs were quiet and oversight was minimal, Clark began testing variations, small changes at first, adjusting carbon content, introducing trace elements, altering heat treatment cycles. Each sample was carefully recorded, each result measured and compared. Most of them failed. Some became too brittle, others too soft. A few showed promise but couldn't maintain consistency. It was slow, repetitive work, the kind that wore people down. But Clark kept going, driven by something most others didn't feel, the certainty that the flaw was real and that ignoring it wouldn't make it disappear. Weeks passed, and then something changed. One of the samples didn't behave like the others. Under stress testing, it didn't crack the same way. Instead of fracturing suddenly, it absorbed more of the impact. Microscopic analysis showed a different internal structure, one that seemed to interrupt the propagation of cracks, preventing them from spreading through the material.
Clark ran the test again. Same result. He refined the composition, adjusted the process, and tested it again. Each iteration brought small improvements, but more importantly, consistency. The material wasn't just performing well once, it was performing well repeatedly. This was different, but it was also a problem, because what Clark had created didn't align with established standards. The alloy composition deviated from what had already been approved for naval use. The manufacturing process required tighter control, different temperatures, and more precise timing. It wasn't something that could be easily adopted without questioning the entire system that had come before it. In other words, it wasn't just new, it was inconvenient. When Clark began sharing early results, the resistance came quickly. The questions weren't just technical anymore, they were institutional. Why change something that already works? Where is the proof that this is necessary? What are the risks of introducing an unproven material? How much will it cost? How long will it delay production? And beneath all of that, an unspoken concern. What if he's right? Because if Clark's alloy solved the problem, then it meant the original design had a weakness. It meant that ships already in service might not be as safe as everyone believed. That was a difficult reality to accept. So the idea was pushed aside. Not rejected outright, that would require fully engaging with it. Instead, it was labeled as experimental, interesting but not practical, worth studying but not urgent, something to revisit later, when time and resources allowed. Later. Clark knew what that meant. It meant nothing would change. So he stopped asking for permission. If official channels weren't ready, then proof would have to come from somewhere else. Clark focused entirely on refining the alloy, treating the next phase like a race against time. He tightened his process, eliminated variables, and built a small but reliable set of samples that consistently demonstrated the same properties. 12 weeks. That's how long it took. 12 weeks of quiet work, undocumented effort, and persistence that no one had asked for. At the end of it, Clark had something no report or calculation could provide: physical evidence, a material that behaved differently, that resisted failure in ways standard armor did not, that could, under the right conditions, do exactly what the Iowa needed: survive the kind of impact that would otherwise tear through steel. But even that wasn't enough, because in a system built on certainty, data alone doesn't change minds. Only one thing does: proof under fire. And that meant the next step wouldn't happen in a lab. It would happen with a live shell, traveling at full speed, aimed directly at the very material no one believed in.
By the time Clark's alloy was ready, there was still no official support behind it. No green light, no formal recognition, no guarantee that anyone with authority would even take the next step. On paper, the material didn't exist. It wasn't approved, it wasn't standardized, and it certainly wasn't something you would trust with the safety of a battleship. But Clark understood something critical. As long as his work remained inside reports and lab results, it could be ignored, dismissed, filed away. But if it survived a real test, the kind no one could argue with, then the conversation would change instantly. So the goal became simple: get it tested. Not in theory, not in simulation, under fire. Arranging that test wasn't easy. Live fire trials were expensive, tightly controlled, and usually reserved for approved materials. Introducing an unrecognized alloy into that process required more than just confidence. It required quiet persistence, the kind that pushes just far enough without triggering outright rejection. Eventually, a small window opened. Limited scope, minimal attention, just enough to run a controlled impact test without drawing too many questions. It wasn't a full-scale adoption trial, but it was something far more important: a chance. The setup was straightforward, at least on the surface. A section of armor plate, produced using Clark's alloy, was mounted alongside a standard plate for comparison.
Same thickness, same dimensions, the only difference was the material itself. If Clark was wrong, the results would be clear. If he was right, the difference would be impossible to ignore. The test range was quiet that day. No audience, no ceremony, just a handful of observers, technicians, and the kind of controlled tension that comes before something uncertain. Then came the shell, a 16-inch round, the same type fired from the Iowa's guns, weighing 2,700 pounds, designed to penetrate heavily armored targets at extreme distances. When it left the barrel, it carried not just force, but expectation. Everyone there had seen armor tested before. They knew what usually happened. Impact, shock, a violent transfer of energy, and then, depending on the material, either resistance or failure. The shell struck the standard plate first. The result was immediate and familiar. The armor took the hit, but not cleanly. Cracks formed, fragments broke away from the inner surface. The energy wasn't fully absorbed, it was transferred violently through the structure. It was the kind of damage Clark had been warning about, not always catastrophic, but dangerous enough to matter. Then it was time for the second plate, Clark's alloy. There was no visible difference from the outside. Same shape, same thickness, nothing about it suggested it should behave any differently. Until the moment of impact. The shell hit with the same force, the same speed, the same conditions. For a split second, everything looked identical, and then it didn't. Instead of cracking in the same pattern, the plate reacted differently. The energy spread more evenly across the surface. The internal structure held together longer. Where the standard armor had fractured, this one resisted. Not perfectly, not without damage, but differently. And in that difference, everything changed. When the inspection team moved in, the contrast became undeniable. The standard plate showed clear signs of failure, fractures, spalling, internal damage that would have been lethal in a real combat scenario. The new alloy, while stressed, remained far more intact, the kind of integrity that could mean the difference between survival and catastrophe. For a moment, no one said anything, because this wasn't supposed to happen. The material that had been dismissed, delayed, and quietly set aside had just performed better than the one already trusted to protect an entire Black Ship class. And it had done so under the one condition that mattered most: real impact. The reaction wasn't immediate approval. Systems like this don't turn overnight, but something had shifted. The tone changed. The questions changed. It was no longer about whether Clark's concerns were valid. Now it was about what to do next. More tests were requested, more data was gathered, and each time the results pointed in the same direction. The alloy worked. Not as a minor improvement, not as a marginal upgrade, as a solution. The kind that forced people to confront what they had previously ignored. The kind that made it impossible to go back to comfortable assumptions. Because now there was proof. And proof has consequences. It meant acknowledging that the original armor had limits that weren't fully understood. It meant admitting that a critical vulnerability had existed longer than anyone wanted to admit. And it meant that the answer came not from the top of the system, but from someone it had almost overlooked entirely. Clark's quiet experiment had become something much bigger, a turning point. And once that door was open, there was no closing it again. Because the next step wasn't testing, it was implementation.
Once the results could no longer be ignored, the conversation changed in a way that few people had expected. What began as a quiet, almost invisible concern had now forced its way into the center of naval engineering decisions. The alloy wasn't just an interesting anomaly anymore. It was a proven solution to a problem that had quietly existed inside one of the most powerful warships ever built. But proving something works and actually changing the system are two very different things. Adopting Clark's alloy meant more than updating a formula. It meant revisiting production lines, retraining personnel, adjusting quality controls, and accepting that the original design, the one already in service, had limitations that needed to be addressed. That kind of shift doesn't happen easily, especially in a system built on precision, hierarchy, and accountability. There were still debates. Some argued that the existing armor was good enough. Others questioned whether the new alloy could be produced at scale without introducing new risks. There were concerns about cost, timelines, and the complexity of integrating a new material into ships that were already operational. But now, those arguments had to compete with something stronger than opinion: evidence. Repeated tests had shown the same result. Under extreme conditions, Clark's alloy performed better. It reduced the kind of internal damage that turned protective armor into a hazard. It held together longer, absorbed more energy, and most importantly, gave crews a better chance of surviving impacts that would otherwise be devastating. In the end, the decision wasn't driven by pride or resistance. It was driven by necessity. Gradually, the alloy began to find its way into production. Not all at once, and not without careful oversight, but steadily. Sections of armor were updated. New plates were manufactured using the revised composition. Standards were adjusted, quietly at first, then more openly as confidence grew. For the sailors aboard ships like the Iowa, nothing seemed different. The steel looked the same, the routines didn't change, the massive guns still fired with the same thunderous force, sending 2,700-pound shells across the horizon. Life aboard the ship continued as it always had, structured, disciplined, focused on the mission. But beneath their feet, around their stations, something had changed in a way they would never see. The armor protecting them was stronger, not just in thickness, but in behavior, in the way it responded to the worst-case scenario, in the way it resisted failure when it mattered most. And that difference, invisible as it was, carried weight. Because in combat, survival often comes down to moments, fractions of a second, the difference between a plate holding together or breaking apart, between damage being contained or spreading into something far worse. Clark's work shifted that balance, not dramatically, not in a way that made headlines or changed the appearance of the ship, but in a way that mattered when everything else went wrong. And yet, for all its impact, his role in that change remained largely unseen. There were no public announcements celebrating his discovery, no widespread recognition, no moment where he stood at the center of attention as the man who had solved a critical flaw in naval armor. The system moved forward, as it always does, incorporating the improvement and continuing on. Clark remained where he had always been, working, observing, solving problems that most people would never know existed. To some, that might seem like a lack of recognition, but there's another way to look at it, because the true measure of his work wasn't in awards or titles, it was in outcomes, in the ships that sailed with stronger protection, in the crews who never had to face a failure that might have happened otherwise, in the quiet absence of catastrophe. Thousands of lives influenced by a solution they would never hear about. And that's what makes this story different. It isn't about a dramatic battle or a single moment of heroism. It's about something quieter, something easier to overlook. A flaw that almost went unaddressed, a system that nearly ignored it, and one person who chose not to. In the end, the Iowa remained what it was always meant to be, one of the most powerful battleships ever built. But behind that strength was a hidden layer of protection, shaped not by consensus, but by persistence. A reminder that sometimes the most important changes don't come from the loudest voices. They come from the ones that refuse to stay silent when something isn't right.